material, the example on sandwich material, then we are going to go into thin wall analysis. Okay, thin wall analysis is just an add-on. It's not more difficult. I'm aware next week, Monday, you'll have thermal fluids. Yes or no? Term test. Okay. And it's a known fact that it's not going to be easy like your term test 1 for your fluid, for your thermodynamics. Am I right? Okay, so spend more time studying for your what? Thermodynamics. Are we clear? If you're not here, you're not here. Are we clear? Okay, so you have to like divide your time. I understand that it's not straightforward. Term test 2 results are out. And I'm happy, I'm really happy. The class average was about 71. And it was not an easy term test. I repeat again, it was not a what? Easy term test at all. And you guys fare so well. I've taught this course. Wait, I'll show you. I've taught this course how many times? If you count the number of files that I have, go on. So I've taught this course 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. I've taught this course 14 times in terms of 3D Mo Circle. This is the best batch. Are we clear? And I'm so proud of you guys. Okay, really, really am proud, and you guys are doing it. Yes. Huh? Beer. I got criticized on ratemyprofessors.com that I give too much beer. Yeah. And I wonder who was it, Okay, so I have to be careful with the beer. I think the Faculty of Engineering knows that I'm giving beer, so I have to be real careful. But anyway, back to square. Hey, listen. You guys put in so much effort. Okay, I can see. Okay, when I grade your final exam, I can also sense it. Clear? Okay, so I have a lot of emails giving to me, Eugene. I'm so stressed now because if I don't pass the final exam, I will fail the course. Okay, keep on hitting this course as hard as you guys are hitting before. Okay, I'm aware that you guys are spending in the library doing nothing but what? BA. Am I right? Okay. Mom, are you okay? You're giving me Kung Fu stroke. Okay? Okay, so I'm aware that you guys are working hard on this, okay? So don't step off, don't let go of the gas, because I can't let things go at all. We clear. Okay? And for the fact that you guys are learning, it's easy, right? Yeah. For the fact that you guys are learning so well, I'm so happy. Okay. Monday, focus on your fluid mechanics. Oh no, sorry, thermodynamics. Okay. I'm going to complete the example on sandwich material. So what we had before, we did this example. Okay. Right. We did this example. And I did both ways, right? We found that if we do from the QZ, and if we were to base on steel, right? We calculated that based on steel, oh, I didn't have my notes here. Did I bring the paper? But anyway, we calculated based on steel is 695.213 times 10 to the power minus 3 inches cube. And if we calculate QZ based on aluminum, the number is 696. Wait, there's something wrong with my pen now. It's 696 times 10 to the power minus 3 inches cube. So the difference by considering the steel or the aluminum, we know that approximately down here, This is our centroid. If we were to calculate for steel, the first moment of area above the centroid has to be positive, below has to be what? Negative. If we just consider aluminum, we just take the area down here. No need to bother about positive or negative. Okay. Now I'm going to write two formulas for you. Okay. And based on bending moment, okay, based on bending moment, we know that stress X is equal to N mz over Izz multiplied by Y. So that is normal stress, and this normal stress is induced by bending moment. And if we look at shearing stress, we have to be careful. In terms of shearing stress, shear XY is equal to Vy over Izz. Okay. Now, the Qz over here will be equal to N with depth Y bar divided by thickness. Okay, divided by thickness. So the difference is this. When you calculate bending moment, the coefficient N over here is on the outside. Whereas over here, the N belongs to the what? Belongs to the first moment of area. And this is in fact equal to N omega dy bar. And this is also our N omega dy bar. Okay. So what I'm trying to tell you is this. You don't put another N outside here. Are we clear? You don't put another coefficient outside the value. Okay. So we know that if you just consider the steel or aluminum, we realize that the first moment of area is exactly the same. So when that's the case, you calculate the shear stress. Okay, so what we are trying to do is we are calculate A. We are determine the shear stress at the bonded surface. So this will be equal at the bond is equal to Vy. Okay, so we know Vy is equal to 4 times 10 to the power 3 given in the question over second moment of area, which we calculate to be 2.0888. And then our first moment of area is 696 times 10 to the power minus 3. And then the thickness, you don't change the thickness is equal to 1.5. Okay. So when that's the case, you have 4 power 3, 696, power minus 3, about 2.088, about 1.5. I got 888. It's a very good Chinese number. Okay. 4 times 10. Hold on, let me do it again. 4 times 10 to the power 3 times by 696, power minus 3. Yeah, 888.88 psi. Okay. So that is one of the value that we have. Okay. So the next thing we're going to do is we are going to calculate the maximum shear stress in the beam. Okay. So the maximum shear stress in the beam, we know that this is our Vy. Okay. The analysis starts from the top. Okay, so this is analysis direction. So the area we have to consider is this whole area. Okay, so this will be equal to, so we want to find the maximum shearing stress. Okay, so if we look at the top, we know that the top, the material is what? We just need to focus on the what? Focus on the steel. Okay, so when we focus on the steel, it's more straightforward. And the reference material we use was steel. Okay, so Q at the centroid is equal to N with depth Y bar. Okay, so N is equal to 1 because our reference material was steel. The width was 1.5. The distance from the centroid from here to here, we found this out. This is equal to 1.232. So this will be equal, the depth is 1.232 multiplied by 1.232 divided by 2. So this will get 1.138 inches to the cube. And then from there on, at the centroid, and the width itself is 1.5. So it's equal to 1.453 times 10 to the power 3 psi. Okay. So now you will have no problem analyzing composite materials, okay, either in bending due to bending moment or due to what? Shearing what? Shearing force. Are we clear? Okay, bending moment was taught by Dr. Koshi in sandwich material, and this is covered regarding the shearing stress. Okay. The most important thing is this. Okay. Okay, that's the most in the N. The coefficient is included in the first moment of area and not outside. Okay, that's the most important thing. Right. The next one that we're going to do is one of the most confusing topic in structure analysis, and only mechanical engineers do it. Okay, people I check, students in civil engineering, they don't do this at all. Okay, so we are going to deal with thin wall shearing stress analysis. Okay. The good news is this, okay, is we have the formula to use, the shear flow, and the shear stress. The formula is exactly the same, okay? And the rules still work, okay? The rule number 1, V and I are what? Constant, okay? Still the same rule. And the second rule is the datum, right? Is at the geometric centroid. Still the same. The third rule is the analysis, right? Starts from the distance, starts from the distance furthest away from the centroid. The fourth rule that we have, still the same. The first moment of area cannot pass the centroid. If you want it to cross, I showed you before, you need to do the plus and minus. Rule number 5 is the Q flow in one direction only. Okay, so these rules still apply, and we have